All right, let's dive in and demystify a really fundamental law of chemistry. But we're not going to start in some lab with beakers and complex formulas. Nope, we're going to start our journey on a mountain.
To really wrap our heads around this big idea, we're going to use a simple analogy. So for a minute, forget about molecules, forget about chemical reactions, just picture something we all understand: climbing a mountain.
I mean, the answer's pretty obvious, isn't it? Of course not. There are tons of ways. You could take a dozen different trails to get to the very same summit. Just hold on to that simple idea, because it's the key to, well, everything we're about to talk about.
So, let's imagine two different paths. Path A could be super short, but man, is it a steep climb. Path B, on the other hand, might be this long, winding trail that kind of meanders its way up. The distance you travel, the effort it takes, totally different. But here's the kicker. One thing is absolutely identical: your total change in elevation. The vertical distance from the bottom to the top is exactly the same. It doesn't matter how you got there, the difference between where you started and where you ended is a constant.
And right here, this is our bridge from the mountain into the world of chemistry. So what if the total energy change in a chemical reaction worked just like that? What if it only cared about the starting chemicals and the final products and not all the messy little steps in between?
Well, as you've probably guessed, it turns out they do. And this whole principle, it has a name. It's a cornerstone of chemistry, and it's called Hess's Law.
The full formal name is Hess's Law of Constant Heat Summation. Kind of a mouthful, I know, but the key words are right there in the name: constant and summation. That's a huge clue that something is always adding up to the exact same amount, no matter how you do it.
Okay, so here's the textbook definition. Now that word enthalpy might sound a little intimidating, but don't let it fool you. Just think of it as the chemical version of our elevation change. It's simply a measure of the total heat energy in a substance. So all Hess's law is really saying is that the total change in energy is the same, whether the reaction happens in one giant leap or you add up a bunch of smaller steps along the way.
So let's boil it all down. The crucial point is this. Just like climbing our mountain, it doesn't matter one bit if a reaction happens in one big step or in a whole series of smaller ones. The total energy you get out or put in will be identical, as long as you start and end with the same stuff.
This brings up a really important question, though. Why? I mean, why does nature even follow this rule? Well, the answer is actually pretty elegant, and it all comes down to a concept called a state function.
Let's really nail this down. Why is chemistry so, indifferent to the journey? Why does it only seem to care about the starting line and the finish line? The reason is, well, it's pretty powerful.
A state function is just a property that depends only on the current state of a system, like its temperature or pressure, not the history of how it got that way. Elevation is a perfect example of a state function. Your elevation on a mountain only depends on where you are standing right this second, not which trail you hiked to get to that spot. And here it is. This is the critical connection. Because enthalpy, that heat energy measurement, is a state function, its change can only depend on the starting and ending chemicals. By its very definition, it's path independent. And that single fact is the entire reason Hess's law works. The law isn't some random rule. It's a direct consequence of enthalpy being a state function. Okay, let's pull all these pieces together. Let's look at the core logic, the most important principle that makes this whole thing tick. The logic flows in a simple four-step chain. It starts with a basic scientific fact. Enthalpy is a state function. Because of that, its change only depends on where you start and where you end. Therefore, the path you take is irrelevant. And that conclusion, well, that is Hess's law. You can see how each idea just flows right into the next. If you take away just one single thing from all this, let it be this. In this area of chemistry, path independence isn't some quirky little exception, it is the fundamental rule. The journey doesn't determine the change in energy, only the destination does. And that brings us to a final, really practical thought. If the total energy change is always the same, what does that actually mean for doing chemistry? It means that if a reaction is too slow or maybe too dangerous or just flat out impossible to measure directly, we can find a different, easier set of reactions that happen to start and end at the exact same places. We can just measure those easy paths, add them up, and get the answer for the difficult one. And that right there is the true power of Hess's law.